Well, hello everyone and welcome to Mathematics Tutorial 6, the first in the Powers series. There'll be 3 of these tutorials on powers. The learning objectives then are to understand the basic nomenclature that relates to the use of powers, so in terms of the base, the index and the exponent, and to be able to manipulate the indices of powers algebraically. So you often see, or you always see, a power in this form, whereby A is the base and B is the index of the base, or its power, and we sometimes see this called the exponent. And we have to have a good understanding of power terms because they often dominate a lot of the algebra that we see in chemistry, and they appear in a large number of equations, and you'll come across them time and time again as you progress throughout your degree. And importantly then, there may be times when we wish to manipulate these powers in an algebraic equation in order to yield the result of a particular experiment, for example. So let's have a quick look at a worked example, a very simple worked example. Take a look at this molecule here, cubane, a very strange molecule, but nevertheless a molecule, a carbon containing molecule. And the length of the carbon-carbon bond in this molecule we will imagine for now is just L. And we're asked to write an expression for the volume of the molecule in terms of this carbon-carbon bond length. And we're asked to identify the base and the index of the expression. So the idea behind this equation or behind this worked example is just to get you comfortable with the nomenclature surrounding the use of powers. So we know that the volume of that molecule can be described, it's a cube, so it can be described by the length of one side multiplied by the length of another multiplied by the length of another. And we can write that as a power as equal to L cubed. Just L times L times L. And here we would describe the base of that power as L and the index as 3. Now, sometimes you will see negative indices, and I use the term indices here as the plural for index. And if you see a negative index, then this indicates that a fraction is involved. If that number after the negative sign is very large, then the number is smaller. We'll describe see how that works in a moment. Let's imagine that you take a conical flask of sulfuric acid at a concentration of 1 mole per decimeter cubed, and that you perform a 10-fold dilution upon that initial flask of sulfuric acid, so that you now have it at a concentration of 0.1 moles per decimeter cubed. Now, simple mathematics will allow you to work out that you've taken 1 mole per decimeter cubed and you've divided that concentration by 10 by the sulfuric acid undergoing a 10-fold dilution to yield a final concentration of 0.1 mole per decimeter cubed. If we were to describe that in an index form, we would call the answer 10 to the minus 1. We've diluted the sulfuric acid by 10 to the minus 1. The 10 tells us that we're working in the base of 10. The minus sign tells us that there's a fraction involved, because remember, a negative index indicates that a fraction is involved. And the index of 1 tells us that the bottom line of the fraction contains 1 instance of 10. So it's a simpler way of representing the calculation that I showed you initially, 1 over 10. Let's have a look at another worked example where we extend this idea. Imagine taking a solution of 1 mole per decimeter cubed of sodium chloride and progressively diluting it. So we take an initial concentration of 1 mole per decimeter cubed and we perform what's known as a serial dilution. We dilute it by tenfold in each step. Well, in the first instance, I've performed a tenfold dilution. I've divided my initial concentration by 10, and I can represent that as a power. My base is 10 and my index is -1. That tells me, again, that there's only one instance of 10 in my fraction. When I perform 2 tenfold dilutions, I would write my fraction as 1 over 10 by 10, but of course a much simpler way of representing that would be 10 to the minus 2 moles per decimeter cubed. And the same holds for the final dilution in this series, which I would represent as 10 to the minus 3 moles per decimeter cubed. So here's a self-test. What I would like you to do is perform the following divisions and express the answer as a base and an index. Answers will be on the next slide. So here are the answers. 1.1, well, 1 divided by a cubed is exactly the same as saying 1 divided by a times a times a, and we can express that as a to the minus 3. The base is a and the index is -3. 1.2, again, very similar. 1 over c squared is the same as saying 1 over c times c. So we can express that as c to the minus 2. 1 over b times b times b is the same as saying 1 over b cubed. So we can express that as b to the minus 3. 1 over d to the 4 is expressed as d to the minus 4. 1 over z to the 3.3, again, can be expressed as z equal to z to the minus 3.3. And 1 over p raised to the power of 4.1 times p raised to the power of 9.2, we first have to collect the like terms. We'll see this in a little bit more detail later on, but here we essentially add the indices, so 4.1 plus 9.2, and we can express that as 1 over p to the 13.3, which is exactly the same as saying p to the minus 13.3. And 1 over d times d to the 4, again, we use our knowledge of collecting like terms and know therefore that that is the same as saying 1 over d to the 5, and we can express that as d to the minus 5. There are a few simple rules to keep in mind when you're thinking about the algebra of indices, when you're thinking about adding them or manipulating equations that involve indices. If you're multiplying terms that are expressed in bases and indices, then you add the indices. So here a to the x times a to the y is exactly the same as saying a to the power of x plus y. If you're dividing terms that are expressed in bases and indices, then you subtract the powers. So here a to the x divided by a to the y is exactly the same as saying a to the x minus y. And finally, if you have a base and an index which is raised to a further power, as in the example here, so a to the x which is raised to the power of y, then you multiply the two powers or indices. So that is exactly the same as saying a to the x times y. So using the rules that you saw on the previous slide, rewrite the following problems and express each in the form of a to the power of b. Answers will be on the next slide. So number 2.1, 10 to the 2 by 10 to the 4. We know that we've got to add the indices here. So that becomes 10 to the 2 plus 4, which is, of course, 10 to the 6. 10 to the 3 multiplied by 10 to the 5. Again, we're multiplying indices, so we know we add them. So it's 10 to the 3 plus 5, which is 10 to the 8. 10 to the 2 divided by 10 to the 4. Well, we remember the general rules that we just showed on the previous slide, and we know now we have to subtract the indices. So this becomes 10 to the 2 minus 4, which is 10 to the minus 2. 10 to the 3 divided by 10 to the 5, again, we're dividing them, so we know that we have to subtract the indices. So here it's 10 to the 3 minus 5, which is 10 to the minus 2 again. Again, we're dividing indices, so we subtract the 2 here. So this is 10 to the minus 2 minus 4, which is 10 to the minus 6. And here we've got a power which is raised to another power, so 10 to the 2 raised to the power of 5, and we know that we have to multiply the two terms here, so this becomes 10 to the 2 times 5, which is 10 to the 10. And similarly, the final answer is 10 to the 30. Now, sometimes you will see indices which aren't necessarily whole numbers. So we've only dealt with indices that are whole numbers so far, and you'll see fractional indices. For example, you might see 1 over 2 or 1 over 3. And here, this implies some kind of root. So a fractional index of 1 over 2 implies a square root. A fractional index of 1 over 3 implies a cube root. And the general rule is that a fractional index of 1 over n implies the nth root. Let's have a look at a few simple examples. 9 to the power of 1 over 2 is equal to 3. So that's the square root of 9. 144 to the power of 1 over 2 is equal to 12, so the square root of 144. 100 to the power of 1 over 2 is the square root of 100, which is 10. And a power of 1 over 3 indicates a cube root. So the usual expression that you might have seen in GCSE mathematics is the cube root of 27. Well, that's exactly the same as saying 27 raised to the power of 1 over 3. Both of those expressions are equally valid when you're describing the cube root of 27. So express each of the following word problems then in the form of a to some kind of fractional index 1 over n, and answers will be on the next slide. So the third root of 27 can be described as, or is an equally valid way of saying that is 23 to the power of 27 to the power of 1 over 3. The square root of 16 can be written as 16 to the 1 over 2. The fourth root of p can be written as p to the 1 over 4. The ninth root of 7b may be written as 7b to the power of 1 over 9. The jth root of 12 can be written as 12 to the power of 1 over j. The ith root of k can be written as k to the power of 1 over I. Okay, and that's all we've got time for today. I will see you in the next tutorial.